Hi, welcome to our first lesson in our second chapter in geometry. Today we're going to be looking at inductive and deductive reasoning, which really are the basis of any kind of proof or logical argument of something that you want to make. You base that on some kind of logical thinking, and the two types that we're going to look at today are inductive and deductive reasoning. Geometry is really a study of mathematics that's based on three not real things, three imaginary kinds of things: points, lines, and planes, which we can't see or touch, right? We can imagine what they look like. However, it's kind of weird to think that the entire study of geometry is based on something that isn't tangible. It can't be seen. Anyway, the foundation of geometry, though, is logical reasoning. And often I think of geometry as the study of why. Why does it have to be this way? What makes it do that? The kinds of logical reasoning that we're going to talk about today are inductive and deductive. Inductive reasoning we use every day. And I got to give you a couple of illustrations, some that are in the flip chart, some that are not. We really do use it almost every day, but you probably don't think about it. This is an example of a conclusion reached by inductive reasoning. My daughter, Allison, petted the neighbor's cat, and she noticed that it purred when she was very young. When she went to her cousin's birthday party the next week, she petted his cat, and it also purred. So Allison, of course, being a very brilliant 2-year-old, concluded that when cats are petted, they purr. Her conclusion then was based on a couple of trials. She looked at what happened when she found a couple of cats and petted them, and she found that they purred. So she figured that must happen all the time, that when you pet a nice kitty, it purrs. That's inductive reasoning. Inductive reasoning makes conclusions based on observing patterns, right? Or looking at the results of trials. Makes conclusions based on observations, patterns, etc. Okay? Makes conclusions based on observations, looking at what's happened in the past and deciding that whether or not that will happen all of the time. Inductive reasoning. I said that I'd add some examples that are not in the flip chart, and this is certainly a place for one. Almost all of us have, if we have a cousin or a younger brother or sister, you've maybe had the opportunity to watch a child as it's learning to walk. That is very much about induction, folks, because what happens is babies are crawling along, and they realize that if they reach their hands up, of course, then they can reach onto a table and maybe pull themselves up, and that's a big discovery for babies. But the whole idea of walking is basically an infant learning that you have to balance yourself or else you fall down. So you'll watch them as they go. They start taking one foot off the floor, and they kind of totter and weave around, and then plop, right down they go. And they'll probably do that 3, 4, 5 times, but finally it gets in there. Hey, you know what? If I put my other foot out in front, that balances me and I don't fall down. Folks, that's inductive reasoning. You look at what happened in the past and you base your future on, or your future reactions to what you've seen. If you're an athlete, you've done the same thing many, many times. And I'm not a great athlete, but I used to play softball. So I think of myself out in the outfield with my glove on my hand, and here comes the fly ball. And the first time that you're out there, you are like, oh no, and it maybe drops, 10 feet in front of you. You don't judge it right. Well, the next time you have a little bit better feel for it. So when the ball comes off the bat, you think, oh, that's coming my way. I better scoot up a little bit. Well, maybe that wasn't the right move. But as you learn the game, you adjust your game by looking at the results of past trials. Folks, that's inductive reasoning, and almost all of us do it every day. One thing that I love about inductive reasoning is that it lets us talk a little bit about series and sequences. So we've got some for you to practice your induction on. As you look at a series or a sequence, what you're really thinking is, how did they get from this one to this one? And maybe you come up with a plan, they added one. And then you think to yourself, but if I add one, that's not right here. So my plan wasn't right. Maybe I better go back. To get from 1 to 2, you could multiply by 2. 1 times 2 is 2. And then you test that. Does that work here? 2 times 2, 4. 4 times 2, 8. Oh, yeah. That's induction, folks. You're looking at how you got from one to the next, and you use that to base future predictions. So I'm thinking that this one is a multiply by 2 or times by 2. And if I wanted to give the next couple of terms then, it says 3, I would do 8 times 2, which is 16, 16 times 2, which is 32, and 32 times 2, which is 64. So we found a pattern, we applied a pattern. Can you do that here? This would be a great time to stop that video, folks, and let's see if we can figure out what's going on. The whole idea of it going from negative to positive numbers in mathematics, there are only a few things that can make that happen, and that's multiplying by a negative. Because if you multiply a negative by a negative, you get a positive. If you multiply a positive by a negative, you get a negative. So this has got to be a multiply by some negative number. Have you figured out yet which number that is? I'll bet you have. Multiplied by negative 3 on this one. 2 times negative 3 is negative 6. Negative 3 times negative 6, 18, etc. Now I'm probably going to have to get my calculator out for this next one, but I know it's going to be positive. Negative times negative. So 3 times 4, 12, carry that. 162 I'm thinking, and I don't know if I want to go any farther without my calculator, so I'm going to grab it right here. In fact, I'm going to check what I just did. 54 times 3, I thought it was. Yep, 162 times 3. That's 486, but it'll be negative this time. And times 3, 1,458. Positive this time. So the only way you can get that jump back and forth between positive and negative is by multiplying by that negative number. The next one, folks, this sequence is so important that it has itself a name. This is called the Fibonacci sequence. F-I-B-B-O-N-A-C-C-I. The Fibonacci sequence. I think it's 2 B's. Fibonacci was a mathematician, and this pattern is so common in nature that it received a name based on Fibonacci's work. Let's see. It starts with 1, and then we have 1. So 1, 1. That's either add 0 or multiply by 1. Adding 0 is not working. Multiplying by 1 is not working here. So it can't be that. Any ideas on this one? If not, then I would suggest take a look at these two terms. Look at that, 1 and 1, and look at the third. And here, take a look at these two, and look at the next. Are you seeing anything there? I bet you are. In order to extend the Fibonacci sequence, we have to add the previous two terms to come up with the new one. So as far as a pattern, we're adding the previous two. And extending this pattern then, the next would be 5 plus 8, which is 13. Then 8 plus 13, which is 21. and 13 plus 21, 34. Folks, the Fibonacci sequence is modeled many times, or it models things that happen in nature. If you split a conch shell, the seashells in Florida, big ones that look like spirals, if you split those, the number of internal chambers inside follows Fibonacci's sequence. It's also true on the outsides of pineapples, you know, the spikes that build from pineapples, the number of spikes in each row increases by a Fibonacci number, at least up to a term. So it happens all over the place in nature. Very, very interesting to look at. These next two, well, these are some of my favorites because they ask you to go a little bit out of the mathematical box. These are the initials of words, and these words are supposed to be familiar to us. I want you to take just a second right now. Don't just listen, but think. M, T, W, common word, she said. And if you're having a hard time with this, let me tell you that the next term in this sequence is T, then F, then S, and S, and then the pattern starts repeating. Oh, that's a good clue. It starts repeating. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and it would repeat from there. One of my favorites, but I'll bet you that gives you a good clue to this one. Let's think calendar on this one. I think I have it. M, J, J. What's the sequence? These are the names of the months: January, February, March, April, May, June, July. So lots of fun when you're looking at sequences with inductive reasoning. It's looking for a pattern, trying to apply the pattern. The second type of reasoning that we want to talk about today is deductive, and that's a little bit different. That's a different style of thinking, not looking at patterns, but instead looking at clues. So I've got a wonderful story that I want to share with you. Detective Darkstone was investigating a break and enter at a local business. He found a crowbar with Snidely Whiplash's fingerprints at the scene of the crime. He followed a set of footprints in the newly fallen snow that led to the Whiplash residence. A search of the house found Snidely playing Halo on a stolen Xbox. Darkstone's conclusion, well, what do you think? Snidely was the thief. Okay? In fact, Snidely was the thief. Deduction is all about following clues, things that are known to be true. Finds a crowbar, has fingerprints, follows fingerprints, right? Those are clues, things that are given information, things that you can show have to be true. Not a pattern, but a clue, a fact, okay? And that probably leads us to the best way to talk about deductive reasoning. In deductive reasoning, valid conclusions are made based on facts and evidence. Right? Facts and evidence. In geometry, in particular, those facts could be given information, definitions, theorems, properties. All of those are mathematical facts. Properties, all of those are mathematical facts. Okay? So let's see if we can apply some deductive reasoning. In Michigan, if you get a high school diploma, then you took 4 years of math. That's the law right now. Julie, who lives in Kalamazoo, got her high school diploma. Therefore, well, what must be true? Is Kalamazoo in Michigan? Did she get a diploma? If those things are true, then Julie took 4 years of math. See, that's deductive reasoning. Based on facts, based on evidence. Kalamazoo is in Michigan. She got her diploma, so she must have taken 4 years of math. Deduction. Here's another example of a slightly different kind of logic stream. If a number ends in 0, then it's divisible by 10. And I want you to think about that for a minute and make sure that you think that's true. 100 ends in 0. Is it divisible by 10? Some people say 0, but 0 divided by 10 is still 0, right? 0 divided by anything is 0. So it still works. This says, okay, so if a number ends in 0, it's divisible by 10. That's the fact. If a number is divisible by 10, then it's divisible by 5. And that must be true as well, because 5 goes into 10 evenly. Therefore, if a number ends in 0, it must be divisible by 5. If a number ends in 0, then it's divisible by 5. Folks, this is kind of again, a logic stream is the way to think about this. We have an if-then statement here, okay? If we end in 0, then we're divisible by 10. The next sentence in this logical argument, and that's what this is, the next sentence in this logical argument starts with this part. If you have some number divisible by 10. So this is repeated here, right? If we end in 0, we're divisible by 10. If we're divisible by 10, we're divisible by 5. So since the end of this sentence and the start of this one have the same fact, a logical conclusion is that you could jump from the first to the last. Folks, this is like the transitive property, and I'm going to write that here because I just want to remind you. Remember, you've learned this before. If A equals B and B equals C, then A equals C. We have the same kind of logic here. This is true. Here we have a repeat. This is true, so we should be able to jump from the first to the last, and that's exactly the kind of logic that was here. A little bit different from this one. In this one, we were presented with two facts. You get that in Michigan. If you have the diploma, then you took 4 years of math. Then we got an example of somebody who lives in Michigan. And then we said, well, that conclusion must be true then, right? Here we had the statement of a fact. If you get a high school diploma in Michigan, you had to have taken 4 years of math. Then anybody who lives in Michigan that has a diploma had to have taken 4 years of math. So they gave us a statement of fact, then they gave us an example, right? Here, there are two different kinds of logical thinking, but both using deduction. Very interesting stuff today. All right, let's go on. Let's see if we do indeed got it. Let's see if we can make some valid conclusions. First one says, if there's lightning, then it's not safe to be out in the open, which is the fact. Okay, we know that that is the truth. Maria sees lightning. Here's somebody who had an example of the first thing happening. She sees lightning from the soccer field, so according to this statement, it's not safe for her to be in the open. Right? It's not safe for her to be in the open. Again, if you think about this style of logic, we get the fact stated here. If you see logic, it's not safe. Or if you see lightning, it's not safe. Then we get an example of someone who sees lightning. Therefore, it must not be safe for them. Deductive reasoning. All right, let's take a look at this one. If a figure is a square, then its sides have equal length. Figure ABCD has sides of equal length. Therefore, and I know that I'm leaning right now to saying that ABCD must be a square. But you know what, folks? If I say that, then I've made a logical error. This doesn't really fit either of our two patterns, I don't think. We have the statement of a fact. If a figure is a square, then its sides have equal length. Then we're given an example but it doesn't tell us that it's a square. See, if this were going to be the first style of that deductive reasoning, it would have to say figure ABCD is a square. It has to repeat back this thing, and it doesn't do that. Let's test the second one. That's the one that first leads to second, so square leads to equal length. Then the next thing should say equal length leads to, and it doesn't do that. This one doesn't fit either. There is no logical or no valid conclusion here. In fact, folks, can you think of other figures whose sides have equal length that are not squares? Yeah, what if figure ABCD is a rhombus, something that looks like the diamond, where all the sides are equal, but that's sure not a square, right? That guy right there, that rhombus, has 4 equal sides, but it's not a square. That kind of reasoning that I just did there, coming up with an example where I get something that has the equal length sides, but I didn't get the square that I was supposed to. That's called a counter example, folks. We found a place where what was supposed to be true wasn't exactly what they thought was going to be true. So a counter example, that's called. And that's probably getting into tomorrow's lesson. But I want to leave you with this thought. I'll come back to my daughter for just a minute. Today's topics have been inductive and deductive reasoning. And in induction, we said that you make your conclusions based on pattern. Okay? In deduction, we make our conclusions based on fact, right, or evidence. And I want you to think about this. After the first 2 weeks of school, and this is true, except that really when Allison was in school, it wasn't chicken bowl, it was chicken nuggets. After the first 2 weeks of school, Allison noticed that the cafeteria had chicken bowls on Wednesday. So she went the first week, and man, she was so excited when she got home. Chicken bowls! They had chicken bowls on Wednesday, you know. She was really excited in first grade. So the next week she comes home on Wednesday and she's like, Mom, they had chicken bowls again! And she was totally into that. So after 2 weeks, she figured that if they did it on 2 Wednesdays, they must do it on all Wednesdays. Do you think that that's a valid conclusion? Can it be proven? Okay, we're in geometry, so we got to know about things about fact. If you've observed it twice, does that mean that it will happen every time? Maybe not, okay? Conclusions based on induction. So I'm going to say it's not a valid conclusion, okay? Because there could be a Wednesday sometime maybe in December, right? Or maybe in November, where instead of having chicken bowl day on Wednesday, they'll have Thanksgiving meal, like turkey on Wednesday. Is that a valid conclusion? No, because there could be. You can't say that that's valid unless you've tested every Wednesday, and you can't test every Wednesday, right? Conclusions drawn by induction. Can sometimes be faulty. Okay? They can sometimes be disproved. Conclusions drawn by induction may, okay, many of them are good, but they may not be always right. And in math, we need things to conclusions drawn from induction may not be always correct. So you got to be careful about that. And I'll leave you with that thought. I'm going to ask you to look at the U-Try on the website tonight. Hope you have a great evening, and I'll see you in class.